Hi, everyone. This recording is to go over our class results for the Enzyme Lab. This will be particularly useful for folks who missed class last week when we did this in class, or if you're working on your Enzyme Lab report and you just forgot some of the things we talked about. This could be helpful to you as well. But this is what we did in class last week. So first, let's remember what this lab was even all about. We were looking at catalase enzyme. We got our catalase enzyme from yeast. Catalase breaks down hydrogen peroxide, which is made as a waste product in cells. So almost all living things make catalase enzyme in order to break down hydrogen peroxide because it's actually harmful to our cells. So we got our catalase from yeast, and we got our hydrogen peroxide from a bottle of hydrogen peroxide. And when we combine those two things, the catalase in the yeast breaks down the hydrogen peroxide into oxygen, which is a gas. So we saw bubbles when it was breaking down our hydrogen peroxide, and water. So this is the reaction that we were looking at. And what we did is we changed 3 different things in order to see how each one of those things affected the catalase activity, or in other words, affected how fast this reaction was happening. So when we looked at pH, and catalase activity is measured from bubbles. So we measured in some cases the height of the bubbles and in some cases the volume of the bubbles. And the more bubbles we had, the more this reaction is happening. So first for pH, let's go over that question. How did pH affect catalase activity? So I want to remind you how you got this data. We did an assignment called Enzyme Lab Pre-Thinking, and in that same assignment you collected data for pH. And the way that you did that is through a video. So what she was doing here is she has different pHs in each of these test tubes. Some are more acidic, some are more basic, some are in the middle. She added the catalase to the hydrogen peroxide in these different pHs, and then you were able to pause the video and measure the height of the bubbles here. That's what you did. So what were our results? If you did this assignment, I told you that it was supposed to look like a curve, whether or not your data actually looks like a curve. If we combined everyone's data in the class, I think we would actually see a pretty clear curve here. Acknowledging that our data was not perfect, this is hard to measure in real life, and on the video it's even more difficult to actually see what's going on. But we got a curve like this. This is called a bell curve or a Gaussian curve, and if you used the template that we gave you for Desmos, one of the choices there is Gaussian curve. So that's the one that you want to use to graph your data. And by the way, if you're ever having trouble with that, you need to make all the things A, B, C, and D all not be 0 before you can see this curve. So just a tip for you. Okay, so these were our results. So how does pH affect the reaction rate of catalase? You could say, as pH increases, the reaction rate increases. Remember, the bigger our foam, the faster that reaction is happening. To about 6.5, pH of about 6.5, maybe 7. I'll let you decide where exactly you think that is. That's the peak of it, and then it starts decreasing again as we increase in pH. So low numbers are acidic and high numbers are basic when it comes to pH. 7 is neutral. So you could describe in your own words what's happening here. How does pH affect the reaction rate? And like we said, the ideal pH is going to be at the peak of this curve here. So the second question we looked at was substrate concentration. So when you actually collected your data, I assigned you either substrate concentration or temperature. So some of you did substrate concentration. And the feedback I got from the class was, there may have been some errors in measuring. We measured using this graduated cylinder. The lines on here are clear. They're kind of hard to see. There could have been some issues measuring. You also measured using your pipette. So depending on how careful you were, you may have ended up with a bubble at the end, which would affect um, how your data collection went, some things like that. But we did not come up with any major issues for the lab. It sounds like it went pretty well. And then just to show you what I did with this data, after you collected data, you submitted it to a Google form, and that all went onto a single spreadsheet that I could look at. So I took your data and I organized it and put it into a graph so that we could see what the whole class found all together. So just to show you, this is what it looked like. We measured a concentration of substrate at 0.5%, so 0.5%, 1%, 1.5, 2, 2.5, and 3%. I'm realizing I'm not sure I fully explained this because when we're talking about substrate concentration, the substrate here is hydrogen peroxide, just to remember that. So the hydrogen peroxide that we got straight out of the bottle was 3%. So the folks that did this kept it at full strength for 3%, and then we diluted it with different amounts of water to get all of these different concentrations. So the one that was 0.5% was mixed with some water. All of these were mixed with different amounts of water to get that concentration. So this is what our data looked like. And when I graphed that, this is what I got. So you might be able to observe right away that we had a very wide range at each one of these concentrations. I can see that we all collected data at 0.5, 1, 1.5, etc. But at each one of these concentrations, there's a pretty big range in the data that we got. So that just makes me a bit less confident in our results, whatever we end up with. It tells me our data collection was not spot on, which isn't necessarily anyone's fault. We were, besides, coronavirus, I guess, doing this from home, we all, maybe people used hydrogen peroxide that was older, in which case it wasn't the actual concentration that you thought it was because it tends to break down a little bit over time. So it was probably weaker than a new bottle of hydrogen peroxide. Your houses might have been at different temperatures. There's a lot of uncontrolled variables that we couldn't control with this online learning situation. So just keeping in mind, we did get a wide range of data. However, I averaged each one of these substrate concentration percentages. And when I did that, we actually got a pretty linear pattern here. So not bad. And that is the pattern that I would expect to see with this. It makes sense that as substrate concentration increases, the reaction is going to happen more and more. The more hydrogen peroxide there is, the more hydrogen peroxide can be broken down. So that makes sense. So I made a line of best fit. I would say it's linear. I made this line and then I was thinking about, should we have a data point that goes through 0, 0? What would make sense? If we have a substrate concentration of 0, that means we don't have any hydrogen peroxide. If we don't have any hydrogen peroxide, you can't break down hydrogen peroxide, so our volume of bubbles should be 0. So I do think this actually should go through 0, 0. I messed up here. I do think this line should go through 0, 0. Just so you know, this was our results from last year when we were in school. We saw substrate concentration increasing to a certain point when it leveled off, which also makes sense. If you imagine what's actually happening here, all of those enzymes are breaking down a hydrogen peroxide molecule one at a time. It does it very quickly, thousands in a second, but it can only do one molecule at a time. So you increase and increase and increase the hydrogen peroxide. You can break down more and more until you get to the point when all of the enzymes are busy breaking down substrate. And even if you add any more, it's not going to break it down any faster. So I think that's why our data leveled off last year. I think this year I just probably used a different concentration of yeast and therefore we had more enzyme. I think eventually if we could have increased the concentration, eventually it would still level off. Okay, so thinking about uncertainty, let's think about what that would look like for each one of these variables. So there's all kinds of rules that you learn about uncertainty and what your uncertainty should be, like depending on the increments you have on your measuring device. There's a way you can do it by taking a bunch of measurements that are measuring the same thing. So we can't do this with this data. But taking a bunch of measurements, taking the range and divided by 2 is another way you can get your uncertainty. But all of these rules are basically a way of coming up with the minimum possible uncertainty. And then if you have reason to believe that your uncertainty should be higher than that, you can always make it higher than that. Uncertainty is really about using your best judgment and having a reason for what you're doing. But there's not always hard and fast rules. So for substrate concentration, the way that we did that was by taking 3% hydrogen peroxide and diluting it. So it had to do with, measuring things using the graduated cylinder. It also has to do with the fact that if you had older hydrogen peroxide, it could have already broken down a bit. So for this one, I really just kind of guessed and said, I think that about 0.5% might be how far we're off on either one of these, on any one of these measurements. So what that means is here, when we're supposed to have 3% concentrated hydrogen peroxide, I'm saying the true value of this data point might be anywhere between 2.5 and 3.5. It could be off by half in either direction. The average volume of bubbles, I have a little bit more logic to it because what we were doing is using this graduated cylinder. And here we have our smallest measurement increment here is 1 milliliter. So whenever you measure using a tool like this, I'm estimating between these lines. So I might be off by up to a half of whatever the smallest increment is. So I would say I'm off by I could be off by up to a half of a milliliter each time I measure. Now, when we measure the bubbles, we actually are measuring the starting point and ending point of those bubbles. That gives me 2 times to be off. So I'm going to take that 0.5 and double it. And so I think at least 1 milliliter is how far we would be off. So I think that would be our minimum possible uncertainty. However, it was hard to read this, especially because our bubble line was not really flat. So I'm going to say we actually would be off more than that. So my estimate was 2 milliliters is how far we might be off. So when I put that into Desmos and added that to our graph looked like this. And again, I do think it should go through 0, 0. But this looks pretty good to me. Knowing that our range was really big for all of these data points makes me less confident. But then again, we did have our averages go through a line of best fit, and all of our uncertainties went through that line, which makes us a little bit more confident. So we did, I'd say, very well for the fact that we all did this from home. Okay, the last question that we asked was, how does temperature affect catalase activity? So what those folks did is they used, I think it was 1.5% hydrogen peroxide the whole time, but it doesn't matter. What they did was they kept their hydrogen peroxide the same the whole time, only they changed its temperature. So they did that by making bowls of hot water and ice water and some in-between water to get these at a few different temperatures. They had a thermometer that they put on a string so that they could actually measure the temperature of the hydrogen peroxide solution and tell us what that was. So some possible sources of error here are all the same things from the first one, but also we measured in Celsius. These thermometers have both Celsius and Fahrenheit on there, so I'm sure it's possible that some folks use Fahrenheit instead of Celsius. That would be an easy mistake to make. Also, when I looked at our data, I noticed some things like this. So 0 degrees Celsius is freezing. So I'm suspicious that someone actually got their hydrogen peroxide down to freezing temperature and even colder. So I think that some of this data is probably not accurate, but I left all of it in so that we could see what we got on a graph, and it looked like this. Beautiful. It looks like a bunch of nonsense to me, but once I averaged it, I just took different sections, like I did 0 to 5 degrees, and averaged all of those temperatures and volume of bubbles, and then I did 5 to 10 degrees, etc. So then I got something that looks like this, which is actually pretty close to what I would expect to see. Because what's happening is as temperature increases, those molecules move faster and faster and faster. And as they do, they bump into the enzyme and substrate, bump into each other more, which is what has to happen in order for those molecules to connect. And so the faster those molecules are moving, the faster they're going to bump into each other, the more often, and the more reaction you're going to have happen. So as temperature increases, our volume of bubble is going to increase to a certain point when it gets so warm that that enzyme is denatured. That means it changes shape and it no longer works with the substrate. So what happens is it increases and increases to a certain point when it then drops off fairly quickly. So yeah, that's what we found for temperature, and that is what I would expect to find. So I talked at you a little bit about why all of these things happened, but you have another assignment called, why we found what we found, or something like that, that's going to go into a little bit more detail about what's actually happening to the molecules in all of these. So do that one if you haven't. Otherwise, yeah, I think you are good to go on this, and you are ready to go on to do your enzyme lab report after.